Well, good morning, dear, and welcome back. So you have started watching videos on genetic algorithm, and we are discussing why genetic algorithm works today, right? Just a little bit recapitulation. Genetic algorithm is a stochastic search method for finding optimality criteria of a function, or in that sense, it is trying to figure out the optimal solution of a function. And the function you may not know, it's so difficult, okay? So in those cases only genetic algorithm will work. And this genetic algorithm, functioning of the genetic algorithm is inspired by organic evolution. The hypothesis is nature, from one cell creature to as complicated machine like human being, nature has created, and throughout that creation, it optimized. Okay, so we want similar kind of thing can we be adapted for genetic algorithm, in silico genetic algorithm. So it is in silico organic evolution methodology is being followed. Specifically, the operator like crossover and mutation. These are the very important operators which in organic evolutions are useful, and in genetic algorithm also they are very useful. And taking a concrete example, I tried to explain that how basic genetic algorithm works. Say I have a function like this, and the variable x varies from 0 to 15, then how to find an optimal solution of this function using genetic algorithm. So that was what I described in my last lecture. So quick recapitulation. So all the integers are to be coded, binary coded. This is binary, by the way, this is binary coded genetic algorithm. There could be other form of codification of genetic algorithm, and genetic algorithm is all about coding and evaluation, right? Gray coded, this is binary coded. So genetic algorithm can also be gray coded genetic algorithm, real coded genetic algorithm, okay, all kind of things. So basic thing we are understanding with the help of binary coded genetic algorithm. So each and every integer is actually 4-bit because 0 to 15, okay, that is a 16 number can be represented by 4-bit. So my codification is I will use 4-bit chromosome, and by the way, 4-bit chromosome, this is called chromosome, and 0, 1, 0, 1, 0, all these are called gene, okay. So here you see all the integers 0 to actually 1 to 15, 0, 0, 0, 0, of course 0 is for 0, 0, 0, 0, okay, I have not written it. So this is actually we are taking the size of chromosome 6, okay, crossover probability 70%, that's 0.7, and mutation probability equals to 0.001, and you know mutation probability is given so that you can get a fresh population. Specifically, it is needed when the search stochastic search is trapped in the local minima or local maxima, okay. So the other day we showed you that, okay, 6 chromosomes you have taken. Who are the 6 chromosomes? So you have all these values, and you have calculated the fitness value of all these chromosomes, right? Which chromosome are to be taken will depend on fitness values, right? So the other day I explained, just watch the videos, right? So 6 is the number of chromosomes, and these are the chromosomes which have higher fitness value. That's why they are here, okay? So fitness values you see is 36, 44, 14, 14, 56, 54. Now we'll have to take a decision that because now you'll have to apply crossover operator so that you can generate through mating the fresh offspring who will be fitter, right? So this is the decision. Suppose, for example, you have decided to take this to be crossed with this, and this 2 will be crossed with 6, and 1 will be crossed with 5, because 1, 2, 3, 4, these are the chronological, if you see, the better fitness values chromosome. So they should get a chance for producing offspring, right? And in that context, the algorithm should run in such a way that average fitness value increase over generation after generation. So this is a higher generation, for example. So you have 1, 2, 3, 4, 5, 6 chromosome with fitness value. So what will be average fitness value? Because this is important, we'll use it, right? So you can just average fitness value if of chromosomes say X. For this kind of symbol we'll use how to calculate it? This plus this plus this plus this plus this plus this divided by 6. So whatever you get, you keep it. And then you also have each chromosome space in the roulette wheel, like here, you see, roulette wheel, right? And this is just like, gamble, you are going to play gamble in Las Vegas. So the chromosome, this chromosome will have better chance, because the wheel, when it is spun, it will rotate, and the indicator have higher probability to stop here, because this is the maximum floor area occupied. This is the maximum floor area, and this is proportional to fitness value. So these are the things which I think is very, very clear to all of you. So this is the role of roulette wheel, right? So that very democratically allow those chromosomes to mate which has higher fitness value. Survival of the fittest, you see, in Darwin's Darwin's theory, right? So, and this way, if you run the algorithm, okay, and you see this being a stochastic search method, if you just calculate it by calculus, is very easy, right? This 50 minus 2x equal to 0, this is giving you x equal to 7.5. So 7.5 is the optimal value, as you know, but genetic algorithm should also give similar to that, because this is only a toy problem which we are using to understand genetic algorithm, as you know. So more or less you have got, if you take the average of this two, okay, so somewhere here, this is 5, 6, this is 7.4 or something like that. So genetic algorithm is working, right? So whatever real value is 7.5, optimal value of x, genetic algorithm is also giving you optimum value of x. So this is crossover operator, okay? So again, 2 is allowed to mate with 6, and then offspring will be, x6i offspring will be 0, 0, and x2i offspring will be 0, 1, 0, 1, 0, 1, and so this place, how many places crossover you will do, it's your decision, right? One decision we took that 70% crossover probability. That means if you have 6 chromosome, 1, 2, 3, 4, 5, 6, so 6 into 0.7, that is 4.2, that means equal to 4. So 4 chromosome we have allowed to mate and create fresh offspring, and 2 other we have kept as clone. Cloning, this is a clone of 2, okay, and this is a clone of 5 because they have, see, they have 2 and 5, 2 and 5. So cloning we are using so that um, fairly high uh, fairly high fitness values they have, so they are there. And others, we are creating offspring by making crossover here in this point. Also, crossover operator can flip 3-bit like this, and then x1 I equals to 1 1 1 and x5 I equals to 0, and it is getting like this. So these are the fresh offspring which you are getting, and plus this. So 1, 2, 3, 4, 5, 6. Again, 6 chromosomes are there. This is very important, that once you have selected number of chromosomes at the beginning of the algorithm, they should be maintained the same number. More chromosome you can, of course, incorporate, better result will be there because a lot of fresh offspring will be there. So stochastic search will be better if randomly you can search. Okay, so that is what you have understood, I think. And then there is one operator called mutation operator. The probability is 0.001 normally we keep, okay, depending upon the problem. So mutation is a dangerous thing, you know, for organic evolution, because once it's a genic change, if the changes in the gene takes place, normally the species does not survive. But if they survive, they give birth to a new, completely new species. Okay, so this is the funda of mutation operator. So mutation will not take place in every generation, right? So you see, out of 6 chromosome, crossover operator is working on 4 chromosomes, right? And so how many chromosomes will be required if 0.001 probability you assign, right? So probability into, right? So equals to, so 1. So probably you required some 1,000 chromosomes. And what does it mean? You know, if 6 is there and 100 generations you are running, so mutation will not take place. Okay, so but mutation to take place, maybe 200 generation you will have to run. So 1,200 chromosomes will be there, and in 1,000 chromosome you apply mutation operator. So that is the meaning of probability assigning 0.001 probability, right? And you see, this is the genetic algorithm cycle. Okay, whatever I was discussing, that in a pictorial form, it has been given to you. A reference, actually, artificial intelligence by Mikhail Magnifiski. So this is crossover operator. Again, so this is a fresh population after ith generation, I plus 1 generation, fresh population you can calculate. Then again, all this population will go to the function, so that fresh fitness value you calculate, and then again you decide that who are the, again 70% is crossover probability, then again you select some 4 chromosomes randomly to mate, and another 2 you can just keep as it is, we call clone. Okay. Then you apply, so sufficient numbers of chromosomes are there depending on what mutation probability you have attached. Then you apply mutation, so that your such probability of being trapped in the local optima will be minimized. So you suddenly change through mutation operator 1 of the gene. Okay, if it is 1, flip with 0. If it is 0, flip with 1, like that. And then again create fresh gene pool, and then calculate fitness value, and then again and again. So this is iterative method till the fitness values are not changing that much. So you can stop. So giving some criteria, stopping criteria, you can stop the iteration. Okay. So this is basically what genetic algorithm is and how it works. So far, listening to the video, you can say, okay, everything is like heuristic, right? And trial and error and all kind of thing. Is it really? No, fortunately, right? So now we are going to discuss what is the theory behind GA to actually work. Okay, that means why GA work? Yes, you're right. We are going to discuss schema theory, and using the schema theory, we will try to tell you that generation after generation, it is who are the chromosomes who will actually survive, and it is the fitter chromosome, fitter and fitter chromosome, the fittest chromosome, which actually survives, because depending on everything depends on the fitness value. Okay, so that is very important to know. And here we have the example we have given with some sporadic examples of chromosomes, right? In a generalized way, henceforth we will try to write, and for that we will try to introduce a concept of schema. Okay, and schemata is actually singular, schema is plural. So what is a schema? A schema is an entity which is defined by defining bits, right? Say I have a 4-bit schema like this, H, right? So this is a generalized representation of the chromosomes, though it can represent so many chromosomes. You see, this star, what are these star? Star can take any value, 0 and 1. Binary coded, we are talking about binary coded GA. So these are called instances of a schema. So it could be, so 1 and 0, they are fixed. So this is defining the schema, okay? So 1, it could be 0, 0, 0, 1 instance, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0. So these are the instances of the schema which is represented by only one H. Okay, so you understand, right? What are the instances of the schema? Maybe beautifully I will write. So there will be so 1, it could be 0, 0, 0. This is one schema. Then another one. You understand, right? So 0, 0, 0, 1, 0. Another one. These are called instances of a schema, right? So 1, 0, 0, 0, 1, 1, 0, 0, and another one is so since I have two bit feature which are free to take any value, 2 square, 1, 2, 3, 4, there will be 4 instances of this schema, right, which is denoted by H. So schema is clearly understood, right? This is a 4-bit schema example. Now we need to know a little bit definition, some useful definition. What is the defining length of a schema? It is the distance between outermost defining bits of a schema. Okay, so the distance between the outermost defining bits. So here, see, these are the star. So these are called defining bit. 1, 2, 3. So outermost, okay, outermost defining bit, the distance. Okay, so this is the distance. 1, 2, 3. So the distance between the outermost defining bit is 1, 2, 3. So LD, that is defining length, will be equal to 3. Similarly, you see, this is a schema. So these are all HI, say. So I equals to 1 is 3. So I equals to 2. Let us see. So you will have to search where are defining bits. So here I could find one, and here is another one, right? So what is the defining length? 1, 2, 3, 4, 5. So you have got. So defining length is 5. Here, what is the defining length? You see, I'll have to again figure out. So I equals to 3. What is the defining bit I could find here? Okay. So 1, 2, 3. Where I should stop? Till I get a defining bit. 4, 5, 6, 7. So if I give any schema, now we are in a position to calculate its defining length. So you see, defining length, smaller or bigger, which is preferable. You see, you will see afterwards, defining length should be very short. Why? Because then the schema has better probability to survive, because you see, when crossover takes place, and you can just, if there is defining length smaller, then it could be spared, no? So if the crossover takes place within the defining length, then that schema will be destroyed. That's the reason that shorter the defining length, better is the chance of it will survive crossover, right? However, the schema will not be destroyed if the two identical chromosome crossover, even when crossover takes place within the defining length, like this, right? If it has a defining length, okay, and if you see that identical chromosomes are crossing over, then even with the defining length, whatever crossover can take place, the schema will remain its identity. Okay. So you have understood what instances of a schema is, what is the defining length, and what is the order of a schema. Say this is a schema. Okay. So order is actually defined as a number of fixed positions in the template. Okay. So how many fixed position on the template, how many bits are there? 1, 2, 3, 4, 5. They are fixed. Only *1 are not fixed, right? They can take any value 0 and 1 in binary coded GA. So order of the schema will be 1, 2, 3, 4, 5. N, it is denoted by N equal to 5. Here, see another schema. What will be the order? 1, 2. So defining bit here are 2. So N equal to 2. And likewise, if I give any schema, seeing the structure or the pattern of the schema, you will be able to tell me what is the order, what is the defining length. Okay. So for example, what is the defining length of this schema? 1, 2. 2 is the defining length. And what is the defining length LD of this schema? 1, 2, 3, 4, 5. Okay. So these are the fundamental things you need to know before we understand the schema theory. Okay. So which we are going to discuss in my next class. So stay tuned. We'll definitely, you will definitely know why genetic algorithm works. This is not, although it's a stochastic search, this is not really completely heuristic. Okay. Okay. Till then, stay safe and have a nice day. Bye bye.